In this sequence of videos, we're going to discuss the graphs of logarithmic functions. Let's start out by graphing a couple different basic logarithmic functions, f of x, which is log base 2 of x, and g of x, which is log base 1/3 of x. And we'll sketch these graphs in two different ways. The first way is we'll make a table, and the second method that we'll use is we'll use the fact that these are inverses of exponential functions. Let's start out by making a table. So let's give ourselves a bit more room, and we'll make a table here of the function log base 2 of x, and then we'll go ahead and plot the points. Now, whenever you make a table to sketch the graph of some function, you have to pick some x values and then evaluate their y values. And the way to pick the x values, there's a tip that you can follow that will enable you to figure out the y values without using a calculator. And that tip is to choose x values that are integer powers, or just integers are just numbers like -2, -1, 0, etc. So integer powers of the base. The base in this case being 2. So I'm going to pick x values such as 2 to the minus 2 because this x value, which is 1/4, is the base to some integer power. Another x value you could choose is 2 to the minus 3, which is 1/8. So I'm going to choose x values like that. I'll start with 1/8, and then we'll go to 1/4, and 2 to the minus 1, that's 1/2, so 1/2. Then 2 to the 0, that's going to be 1. 2 to the 1 is 2, and 2 squared is 4, and 2 cubed would be 8. So I'm going to make these my x values. 1, 2, 4, 8. Now you're going to see why I chose these x values in just a moment. Let's say we want to evaluate log base 2 of 1/8. So we can start filling in our table. So log base 2 of 1/8. If we set that equal to y and convert to exponential form, that means that 1/8 would be 2 to the y, which means that this y would have to be -3. So log base 2 of 1/8 is -3. So this is going to give you some practice on evaluating logarithms from a previous section. If you wanted to do log base 2 of 1/4 to fill in your table, you can set that equal to y, convert to exponential form, and we get that 1/4 is 2 to the y, which means y would be -2. So the y value for 1/8 is going to be -3, and the y value for 1/4 is going to be -2. So let's go ahead and fill that in, -3, -2. I'm going to fill in one more here, so let's figure out what the y value is for x equals 1. Log base 2 of 1 equals y. We switch to exponential form, and we get that 1 is 2 to the y, which means y is 0. So for the x value of 1, y is going to be 0. And now, if you'd like to as an exercise, I encourage you to find the y values for the rest of these. I'm going to go ahead and fill in what the results are. And now perhaps you can see why I chose x's to be powers of 2, because it makes these y values here very easy to figure out. If you don't choose your x values carefully as powers of the base, then it becomes very challenging to evaluate log base 2 of those x values without using a calculator. Let's make a table for the other function that we have here, log base 1/3. So there's my x's, log base 1/3 of x. And again, I'm choosing x values that are powers of the base. So for example, 1/3 to the -2, I'm going to pick that as one of my x values. So this ends up being 9. So 9 is going to be one of my x values. 1/3 to the -1 is going to be 3. And I'll let you work out the details of figuring out that 1, 1/3, and 1/9 are also x values that you can choose. And if we go to figure out the y values for these x values, then log base 1/3 of something like 9. If we wanted the y value for x equals 9, then we set this equal to y, convert to exponential form. And this means that y would have to be -2. This step here, you may notice that it is in some way mirrored from our choosing of the x values. But in the end, we have that the y value for 9 is going to be -2. And I'm going to fill in the rest of the y values here. And I strongly encourage you to double check them. So now we have a table, and we can go ahead and sketch the graph of these functions. So let's go ahead and do that. Some axes, I'll need x and y's, and we'll fill in a scaling here. Let's make this 1 and this 1. And we'll need quite a few x values all the way up until 8. So 1, 2, 3, 4, 5, 6, 7, 8, and actually we'll need up till 9 because of the graph of log base 1/3 of x. And the y values, we won't need quite so many. Let's fill in up to 4. We will need some negative y values. -1, -2, -3. And now let's start filling in log base 2 of x. So for x equals 1/8, which is very close to 0 here, we have a y value of -3. For x equals 1/4, which is also close to 0, we have a y value of -2. It's a little hard to draw because it's so close to the y-axis, but I think this is a reasonable drawing here. So at x equals 1/2, we have a y value of -1, and at x equals 1, we have a y value of 0. At x equals 2, we have a y value of 1. And at x equals 4, we have a y value of 2. And finally, at x equals 8, 1, 2, 3, 4, 5, 6, 7, 8, we have a y value of 3. And we can go ahead and connect this with a smooth curve. It looks something like this. Let's sketch our log base 1/3 of x on the same graph here. At x equals 9, which is the very last tick mark that I made, we have a y value of -2. At x equals 3, we have a y value of -1. At x equals 1, we have a y value of 0. At x equals 1/3, which is, that's where x equals 1/2, so maybe a little bit smaller than that, we have a y value of 1. And at x equals 1/9, we have a y value of 2. And the graph of this will look something like, trying to get as close to the y-axis here as possible. I think maybe one more shot. There we go. We have something that looks like this. Pardon my unsteady hand here. Should be a little smoother. There we go. I think it's worth pointing out here that both of these graphs go through the point 1, 0. And the reason is because if you take log base b of 1, you will always get 0, because when you convert to exponential form, you get that 1 is b to the y, and that means y would have to be 0. So any function, any logarithmic function with base b that looks like log base b of x will go through the point 1, 0. This is analogous to the fact that every exponential function will always go through the point 0, 1. Now, another way of explaining the fact that all of the logarithm functions go through the point 1, 0 is remembering that logarithms are inverses of exponential functions. So log base, well, let's use a concrete example for b. Log base 2 of x is the inverse of 2 to the x. And remember, to graph the inverse, we just switch all of the coordinate pairs on the graph of the original function. So since 0, 1 is always on the graph of the exponential function, so in particular, 0, 1 is on the graph of 2 to the x, we would know that 1, 0, that is the point where we switch the x and y, 1, 0 is on the graph of the inverse of 2 to the x, which is log base 2 of x. And this actually leads nicely into discussing the other way to graph these logarithmic functions. So if you want to graph log base 2 of x, one thing you could do is you could create the graph or create a table of 2 to the x. So -2, -1, 0, 1, 2, and fill in the y values, which it's easier to fill in the y values for this exponential function. Then if you want to graph the inverse of 2 to the x, which is log base 2 of x, we simply just switch all the x and y values. So 1/4, 1/2, 1, 2, 4. I just copied all of the y values, and now I'll copy all the x values over to here. So -2, -1, 0, 1, 2. And you could graph or create the table for the graph of log base 1/3 of x just as well. You could create a table with the x values of -2, -1, 0, 1, 2. Then fill in the y values for 1/3 of x here. And then switch the x and the y values to get a table for log base 1/3 of x. So that gives you a couple different ways to create the graph that we have here. Let's clean this up a bit. And now that you have the graph, you can make some basic observations that we've already stated in previous sections, corresponding to information about the domain and the range of the logarithmic functions. So if you have a logarithmic function, which is log base b of x, from this graph, we can see that the domain is all the positive numbers because 0 and the negative numbers have no y values above them. And the range is all real numbers. Of course, the reason for that being, if you draw a horizontal line at any y value, you're going to get an intersection with the graph somewhere. Now, we don't see the intersection for this y value that is quite high, but the graph will intersect this y value eventually. So the y values that are attained by the graph are all of them all real numbers, so the range is all real numbers, which is something we had already established, but worth noting.